Yeah, good morning, Munich. Thanks for coming and welcome to Indirect Syscalls, a journey from high to low. As already mentioned, my name is Daniel Feichter. I'm from Innsbruck and the founder of Red Ops Information Security, with which I mainly focus on offensive security stuff. And today we will take a closer look at direct syscalls and indirect syscalls. This talk will cover system calls in general in Windows OS, why are they necessary, how they are used in Windows. Then we will speak about direct system calls, why the red teamers use them or no longer use them at the moment, and what is the concept of direct syscalls. We will also speak about indirect system calls, why red teamers switch from direct syscalls to indirect syscalls, what are the limitations of indirect syscalls. We will also build step by step our own indirect syscall shellcode loader. And at the end, we will also talk a bit about how the EDRs can use Event Viewer for Windows, ATW, to detect or prevent direct and indirect syscall execution, and also compare the threat stack, call stack from different shellcode loaders. Okay, so chapter 1. Windows OS system calls. So, for what are they responsible? When you imagine you have an operating system like Windows, you have your user mode and your kernel mode. And if you want to switch or make a transition from user mode to kernel mode, we need system calls. So, system calls are necessary, for example, to access parts which are placed in kernel, like hardware, device drivers, scanners, printers. If you want to save a file, you need temporary access to the file system. Therefore, we also need system calls. So, what is a syscall or system call? When you want to take a look at the syscall instruction, you can use a debugger like WinDGB and search for a native API like NT-allocate virtual memory, debug it, and we can see that we have in the second line a move instruction which puts the number 18, which is the syscall number, or also called system service number, into the register EAX, and then we have the syscall instruction which executes the syscall or the syscall number. Very important, each syscall has a specific ID which can switch from Windows to Windows and also from version to version, so they can differ. A practical example, when we use system calls, so, for example, you have Notepad open, you type in something, you want to save it to disk, then you need, or the operating system needs temporary, or the process, more specific, needs temporary access to the file system in kernel, and also to the required device drivers. And both components are placed in the Windows kernel. That's the reason why we need system calls to make that temporary transition. So when we take a look at this illustration, we can, on the upper side, see the Windows user mode, at the lower side, Windows kernel mode. We have on the left side, notepad.exe, and we want to save a file to disk. So we first have to access the Windows API or Windows 32 API, which is always located in, or could be located in kernel 32 DLL or kernel-based DLL. Then we want to access the corresponding native API, which is in this case NT-create file, and is located in the memory area of NTDLL. And the native API contains then the syscall stub, which also includes the syscall number or the syscall instruction itself, in the red case. And yeah, those are the instructions which we use to make that temporary transition from user mode to kernel mode. So in summary, we can say every syscall has a specific ID. It can differ from Windows to Windows. The syscall stub is retrieved from NTDLL, and the system call itself is part of the syscall stub. And it gives us the possibility to enable temporary privileged access to kernel mode to access device drivers or file system, for example, when you want to save a file. So we now get briefly understanding for what system calls in Windows are used, and now we want to try to understand direct system calls. So direct system calls are, I would say, were a common red team technique to, for example, execute malicious code, to use it for shellcode execution, or also to use it to dump the alphas process, like the tool from Outflank, which is called Dumpert. And it simply said it allows us the execution of syscall or the execution of the syscall stub without using or accessing NTDLL. Hence also the name direct syscalls. So when we take a look at this illustration, we see compared to the Notepad process, we have our malware.exe, and we do not want to retrieve the system call or the syscall stub from NTDLL. Instead, we want to directly implement it into the assembly itself. Therefore, we have our 4 lines of code directly implemented as assembly code into the shellcode loader itself. So the question is, why would we need or why do we use direct syscalls? The answer is very simple. When you have, or most EDRs in the time, or many EDRs use a technique which is called user mode API hooking, and this technique gives the EDR the possibility before the syscall is really executed to redirect the executed code in context of a Windows API to analyze it. And to check if we are executing malicious code or not. They can use, or EDRs use, different kind of hooking techniques. So before PatchGuard, it was also possible to use kernel hooking techniques like SSTD hooking. There are still some vendors which use a PatchGuard bypass to use that kind of technique, but most vendors are, I would say, forced into user mode by PatchGuard and use most common technique, which is called inline API hooking, which is simply a 5-byte long unconditional jump instruction and redirects the code to the DLL of the EDR. So we can see this in this illustration, again, on the upper side user mode, on the lower side kernel mode. Our malware we will execute Windows APIs in our malware. So we have access kernel 32 DLL, kernel base DLL, and then we need the corresponding native API in NTDLL. But now we are not directly executing the syscall stub or the system call instruction because the executed code is now first redirected to the EDR DLL. So the EDR does inject into user mode in every process his own DLL, which we could also name hooking DLL. And if the EDR says, okay, the code is malicious, then he will stop the execution. If the execution is fine, or the EDR is fine with the execution, we jump back to NTDLL and then execute the syscall instruction. So where are now those EDR hooks? When they started using EDR or user mode hooking about, I would say, 6 or 7 years ago, mostly they placed their hooks in NTDLL. What's the reason for that? Because NTDLL is more or less the lowest common denominator before you make the transition from user mode to kernel mode. But in the meantime, when you analyze different kind of EDRs, you will see that they also use now hooks in other DLLs like the Win-INET DLL or the Win32U DLL and many more others. Depending on the EDR, it can be that the amount of hooks depends strongly on the EDR. So for example, you can have an EDR which has about 28 user mode hooks, but I also analyzed EDRs which have 86 user mode hooks in user space. So the question is now, are we fucked up by hooks? I would say no, because they cannot simply hook all native APIs. This is simply a resource problem, costs time, and would slow down the operating system. And generally, when you analyze an EDR, you will see that they mostly focus on API calls which are heavily abused in malicious contexts like NT-allocate virtual memory and similar API calls. If you want to check out how does an inline hook look like, you can use also a debugger like WinDGB. So on the lower illustration, we see a clear syscall stub, I would say. So we have around the red line, we see that we have a move instruction which puts again the syscall service number, in this case 18, into EAX register, prepare it for execution. And when you have an EDR which hook this API on the upper side, we see that the second line, the move instruction, is replaced by a 5-byte long unconditional jump instruction. And this is the jump which is responsible for redirecting the executed code in context of the API to the DLL from the EDR. So what are now the consequences for red team? Hooking makes it more difficult to execute malicious code, such as shell code. And we as red teamers can think about different techniques to bypass EDR. So we can search for not hooked APIs. We can try to use user mode unhooking. We can try to tamper in EDR. And we can use techniques like indirect syscalls and direct syscalls. And in this talk, we will focus on direct and indirect syscalls. Okay, with chapter 3, we will start developing our indirect syscall shellcode loader, and we start with a simple Win32 API loader. This will be our reference loader, so from evasive perspective, a Windows 32 API loader without using additional unhooking is not really useful for EDR evasion, but it serves us simply as a reference loader. So when we take a look at this illustration, we have on the left side our Win32 API shellcode loader. We use 4 APIs in this loader, and because we are using Windows APIs, we have to ask for the Windows API virtual alloc, for example, in kernel 32 or kernel-based DLL. Then we need the corresponding native API anti-allocate virtual memory in NTDLL, and then we can execute the syscall stub from the text section or the memory in NTDLL. So what do we need in our loader? We have to declare our shellcode. We need a possibility to allocate and commit memory. In this case, we are using virtual alloc. Then we want to copy the shellcode by using write process memory into memory. We want to create a new thread or execute the shellcode by creating a new thread. And we want to wait until the shellcode execution is finished, until the main thread can then exit. And therefore, we use the Windows API wait for single object. So in summary, we can say, as already mentioned, as from the evasive perspective, not really useful, as until the point you would combine it with a technique like user mode unhooking. But in this case, it serves simple as a reference loader for us. So in the next step, we want to make the transition from high-level APIs, from Windows APIs, to medium-level APIs, to native APIs. So this is the first modification to our Windows 32 API loader. And we want now to avoid that we ask kernel 32 DLL or kernel-based DLL for the Windows API and directly implement native APIs into our shellcode loader. So when we compare this illustration with the illustration before, we see that we now do not have longer in kernel 32 DLL and kernel-based DLL involved. Instead, we want to directly ask NTDLL for the respective native APIs which we need in our native API shellcode loader. Compared to our Windows 32 API loader, we have to manually define the instruction for the function pointers in our shellcode loader for each native API. And in the second step, we have to ask NTDLL, or we need to get the memory address for each native API. So the first step, we have to use the Windows API get module handle A to open a handle to NTDLL. And then we use get proc address to get the memory address for the corresponding native API. And we simply want to replace all Windows 32 APIs against the correlated native APIs. In summary, we can say that we have made the transition from Windows 32 APIs to native APIs. We do not longer import Windows APIs by using kernel 32 or kernel-based DLL. And if an EDR would now theoretically only set his hooks in kernel 32 DLL, we would have bypassed EDR. But in practice, this is not really the case. So we have to go forward with our development process. So in the next step, we want to make the transition from native APIs one step lower to low-level APIs to direct syscalls. So we want to build a direct syscall loader. And compared to the reference loader, we will do now our second modification. So we want now to reach the goal that we do not longer ask NTDLL for the syscall stub or the syscall instructions. Instead, we want to directly implement the needed syscall stub or code into our direct syscall shellcode loader. So when we take a look at the next illustration, we see that we now have no longer involved NTDLL. Instead, we directly search for or implement the syscall stub, those 4 instructions, directly into the text section of our assembly. Again, we want to use native APIs and do not want to ask, but compared to before, we want not to ask NTDLL, so we directly implement it, and we have again to manually define the instruction pointer as in the native API loader. But now we want to directly implement the assembly code, which we need. So we can see in the illustration, this is one of the syscall stubs, in this case for the native API NT-allocate virtual memory. And we directly implement it into the text section of our shellcode loader. Because we are doing this in Visual Studio, we also have to enable support for Microsoft Assembler. And from a perspective of EDR hooking, this loader would be fine. So a few years ago, direct syscall loaders or direct syscalls in general worked very well against EDRs. But the problem now is that most EDRs also use event tracing for Windows. And when they, for example, analyze the thread call stack from your direct syscall loader, they will catch you. Why? When you take a look at the right side, we have the call stack from our direct syscall loader, and on the left side from the Windows 32 API loader, which has a very high legit call stack. And we can see on the right side that the call stack from the direct syscall loader looks very weird. For example, the last element, NT-wait for single object, is executed from the text section of the shellcode loader itself. And that is a 100% IOC because the syscall instruction or the API should always be executed from NTDLL, which means normally NTDLL should be the last element on top from the call stack. So that's the reason why we have to switch to or make the next transition from direct syscalls to indirect syscalls. So this is our third modification compared to the reference Windows 32 API loader. And we want now to reach that the IOC switch an EDR can use to catch a direct syscall loader, that we are able to spoof the syscall and the return address. So it's mostly the same code as a direct syscall loader. We have just a small change. When we take a look at this illustration, we see, for example, for NT-allocate virtual memory, that after putting the system service number into the register EAX, we do not directly execute the syscall and the return instruction. Instead, we use a jump, an unconditional jump, and jump into memory of NTDLL. By this, we can reach the goal that the syscall instruction and the return instruction is not executed in text section of your shellcode loader itself. Instead, it is executed in NTDLL, and this gives us the advantage that now NTDLL is put on top of the stack from your shellcode loader or from your thread, more specific. So we have to manage the syscall and return instruction. Therefore, we have to do a few things. We have, again, to open a handle to NTDLL. Then we need to get the start address from native API in NTDLL. We have to set the offset to get the memory of the syscall instruction, and then store that memory address in a global variable. And we have to do this for each native API which we use in our shellcode loader, so 4 times in this case. So again, we use get module handle to open a handle to NTDLL. Then we use get proc address to get the start address of the function. But now, because we want to get the memory address of the syscall instruction, we have to set or to add an offset of 12 bytes. Why 12 bytes? Because that's the offset to get the memory address of the syscall instruction in the syscall stub. Then we can declare a global variable to hold the memory address of the syscall function and then later use it in our assembly code, in our loader for execution. And there you can see a comparison. On the left side, we have the syscall stub from our direct syscall shellcode loader, and on the right side from the indirect syscall shellcode loader. And in the third line, we have this small difference. The syscall instruction is not directly executed in the text section. Instead, we use this unconditional jump and jump to the memory address from syscall in memory of NTDLL. Also in this case, again, we have, because we do this in Visual Studio, we have to enable Microsoft assembler support. And when we now compare it, the call stack from the shellcode loader, you can see that the indirect syscall loader has a much more legit call stack compared to the direct syscall loader. Why? Because here the last element is the wait for single object or anti-wait for single object API, and is not executed now from the memory of the syscall loader itself. Instead, we jump to NTDLL as it should be, and then execute it in this memory. So also when we compare it with the indirect syscall loader on the right side with the Windows 32 API loader on the left side, we see that the indirect syscall loader has a very high level of legitimacy, I would say. Okay, in summary, call stack analysis, we can say that indirect syscalls can be used to, or a good development, further development from direct syscalls, but also indirect syscalls are not a silver bullet. Also, indirect syscalls, when you build up your own shellcode loader, can be just a part of the puzzle. So you also have to care about other things like encryption, import table hashing, you have to care about obfuscation, you have to care about maybe hardware breakpoints. So this is just a part and not a silver bullet. And even, or depending on EDR, it could still be that you get detected by analyzing the call stack. Why? There are also some EDRs which do not just check for if the syscall is executed in the right location. They also can, or also check, for example, Microsoft Defender, ATP, if the whole call stack is legit. So they, check the whole call stack. If you want to learn more about threat call stack spoofing in general, so this is outside for this talk, but there is a very nice guy or clever guy, which is called Alessandro Magnosi, alias Kletzvirus, which do a lot of great work in that area. He also, for example, developed SysWiz 3 and gave this year a very nice talk about call stack spoofing on DEF CON. So I highly recommend to check this out. Okay, in summary, we can say indirect syscall loaders, we make successful transition from direct syscalls to indirect syscalls, and we do now just partly execute a part of the syscall stub from the text section of the direct syscall loader and jump on the right time to the memory address from NTDLL. Okay. So in summary, we learned a bit about Windows syscalls, about the concept from direct syscalls. We started building our own indirect syscall loader. So we started with a Windows 32 API loader, which is more or less our reference. Then we make the transition to a native API loader. We built in the next step a direct syscall loader, then an indirect syscall loader. Did a bit call stack analyzing, and so far so good. So this was very fast. If you want to do all that stuff in much more detail, I built up a repository which was presented a few months ago on DEF CON 31, which is a very detailed workshop where you can read all about that stuff in much more detail and develop your indirect syscall loader and debug it step by step. So at this point, many thanks for your attention. Many thanks to the whole team from B-Sides and all volunteers and all sponsors for the organization. Really great event, and have fun with the rest of the conference. Thank you.
Thank you. Thank you very much for the call, for the talk. Any questions from the audience?
Hello. Maybe this is a stupid question because I come more from the Linux side. So I'm a little surprised. Has the Windows kernel no event framework that you can just say, every time a process is enter kernel mode, give me an event, then you can avoid all the hooking. For example, on Linux, I just enable a trace point for a system call gate, and then user space can do whatever they want, and every time they enter the kernel, I get a kernel event.
It could be that Windows event tracing has such events. I'm not aware about it at the moment, but I think they definitely have it because, as already mentioned, EDRs use it also to check where the syscall is executed from. So I think there have to be a mechanism like that they can use ATW to check those events, yeah.
Okay, thank you. Any other question? I think we have time for one more question.
Hi, thank you for your talk. The problem we're having usually when we're trying to evade EDRs is that we don't know which functions are being hooked or which kind of telemetry that is being sent to the EDR. So in your experience, is there any kind of project, a public project, a repo that would have some information about multiple EDRs regarding the, let's say, the detection of these techniques?
So in general, the problem is that EDR vendors are very sensitive about that. So I personally have a private repository where I collect those information, but I cannot release it, otherwise I get problems with the vendors. But there is a repository, I think, from Mr. Unicoder, which collects, for example, which hooks or which APIs are hooked by which EDR, but I'm not sure if it is at the last, if it is the last version from the hooks which are set. This is one of the repositories which I know. So as I remember, I have one, but will not release it. Otherwise, I get again problems.
Okay, thank you very much again for the great talk. I'm sure he's available for further questions in the lobby. And thanks again.
Thank you.